Okay, we're going to look at levers and how levers work. So the image in front of you has the Minotaur on the right and Achilles on the left. And you can see that they're on a seesaw, and the seesaw is tilting in favour of the Minotaur. Now what that would mean is the Minotaur's moment is greater than Achilles' moment. And if Achilles wanted to make the seesaw rotate anti-clockwise, he'd probably have to move further away. You'll also notice there that there's a circular disc in the middle. That's your pivot point, that's your rotation point, that's your fulcrum. So a lever will use this idea that you can have moments on either side, and the larger moment will cause a rotation in that circular direction. So the definition of a lever there is a rigid body that's free to rotate about a fulcrum. And it's one of the simplest machines that we know as people. So if you look there, we've got our pivot point, which is the stone, that's our fulcrum. Then to the right of it, we have a short distance, and then on top of that, we have a load. And that load there has a lot of force in comparison to the effort that the girl is exerting, as evidenced by the blue arrow, which is larger than her yellow effort arrow. The girl then is exerting a smaller effort, but the distance that effort is from, the distance that effort is from the fulcrum is much, much larger. And if the moment caused by her effort is larger than the moment caused by the load, it will cause an anti-clockwise rotation, and that load will be lifted up, or it'll be tilted and allowed to roll to the right. So a lever is just a body that does that. It lifts up an object by you exerting an effort that's a further distance from the fulcrum than the load is from the fulcrum. So this is another example. We have a stone on the bottom left-hand corner, and the distance of the force caused by the presence of the stone from the fulcrum is quite small, and then the lady is just using one hand with a small force, but the distance is very large. The moment caused by the lady's force is much larger than the moment caused by the stone's force. As a result, we get a clockwise rotation, and the stone is lifted up. Okay, so here are some examples of levers. A hammer taking out a nail, you can see the fulcrum and the effort. Again, the effort and the effort's distance are much larger than the load and the load's different distance multiplied together. Same with the scissors. And then we have things like chopsticks, nutcrackers, and also this ancient machine which was used for lifting heavy objects or transporting water from one place to another, perhaps as part of an irrigation of a field. Okay, so the next question then is, could the person actually lift the car? So you can see the back wheels are rising. I'd like to know, is it true or is it false? But I want to go one step beyond that, and I would like you to calculate a value to prove that it is true, if you believe it's true. What that will entail is you will need to get the weight of a standard man, you will need to get the weight of a car, and you'll have to suggest a length for that beam. Okay, pause the video and do it. I'm going to keep going. Okay, the next thing I want you to do is research the 3 types of levers in the human body, and for each of those type, I want you to name a part in the human body where that lever exists. Also, if you can find an image or draw a quick diagram of it, I'd like you to identify where the fulcrum is for that lever, and usually where the load is in each case. That image, by the way, is out of bounds, so you're going to have to find 3 different images.